Source spaces define where you expect your sources to be that you want to estimate from your EEG and MEG data. So it's often a cortical surface, but it doesn't have to be. So in Python, at least, we often use these cortical segmentations that come from FreeSurfer. Now, to visualize them, we sometimes have to, or we often inflate them so we can look inside the gyri. So that is quite a powerful way to model EEG and MEG sources, especially since we mostly see the cortical sources. I mean, they're the ones that are closest to the sensors. You can include subcortical sources, a few words on that later, but most of the time, I think we are mostly interested in the cortical sources. If you don't have individual MRI images, there are standard head models, including cortical surfaces. Software packages, some software packages like SPM use a canonical mesh. That means more or less the same cortical surface for every participant, can just be adjusted a little bit individually. That makes it a bit easier than to compare these solutions across participants and group statistics, for example. I mean, that is something you will have to check in your individual software packages. You will have to somehow normalize your cortical or your source spaces one way or the other if you want to do group statistics or you want to average them across participants. For example, in Python, you use the FreeSurfer method of projecting your cortical surface to a spherical representation. And then there are clever ways of morphing these across participants sort of into the same space. And once you've done that, you can deflate again into the original space, and then you have cortical surfaces that are aligned to each other, and you can average them with the group statistics across participants. One question you have to ask yourself at the beginning: how many dipoles do I need? Well, you want to have enough so that you sample the distribution with enough accuracy, but if you have too many, this can slow down your analysis. Standard choice in MNE is about 10,000 vertices, or maybe 4,000 to 5,000 per hemisphere, and that's more than enough, I would think, for most applications. So it actually smoothes the cortical surface a bit. So this would be the one as it comes from FreeSurfer with 8,000 vertices, and you can see you lose a little bit of detail, but considering that spatial resolution of EEG and MEG is not that high anyway, this should actually be enough for most applications. And there are software packages that even use fewer. So you may have one or a few thousand vertices across the whole brain, considering you only have a few hundred sensors. This should usually be enough. You don't have to use the cortical surface, so you can use volumetric source spaces. That means you put dipoles all over the three-dimensional volume of the brain. For example, if for whatever reason you don't have cortical segmentations or you can't really accurately get them from your data because you have patients with brain damage. So that's when you can use these volumetric source spaces. In general, I would say use every constraint you can get to make your inverse problem less non-unique. So I think it's reasonable to constrain your sources to a cortical surface if you have it, but often in software packages you have the choice. Sometimes you have the choice to choose something in between. So you have a volumetric source space, but you only use sort of a volume around the gray matter. So these are options that you may have in different software packages. If you're interested in subcortical sources, then you have to spend a bit more effort. I mean, you have to, first of all, get your subcortical structures from your MRI images, either from individual MRI images, standard head models. So in this case, the cerebellum, you can get that. You just have to spend a little bit more time on your data processing there. Also, the data visualization might be a bit more complicated. So in this case, this comes from an Python tutorial or example. So you then visualize, your source estimate here on the cortical surface, as well as in the subcortical area in the cerebellum as well. I don't know if you can actually see anything down here, because there are some dipoles floating around there. So it's possible, just a bit more work, and you have to decide whether it's worth it to you. And finally, we have to deal with source orientations, because currents have a direction or an orientation. So in this visualization, you can see that every source, every dipole is visualized as an arrow. Yeah, I mean, every current at every location, can flow in different directions here. So we usually ignore that and we just look at intensities, and basically the length of these dipoles. And then we just want to know whether it gets bigger or smaller depending on our experimental manipulation and compare that between conditions. But in principle, there's information about orientation as well. And we have different options to model that in our data. We can, right from the beginning, say, yes, our currents can go in any direction. So we can model them as free dipoles, or sometimes also called rotating dipoles. So every direction has equal importance here at every location. But certainly the most liberal approach. But you might say, okay, I want to use every constraint I can get. And we know that usually our dendrites are aligned perpendicularly to the cortical surface. So that means the currents will mostly flow across that into that direction. So I can fix my dipole orientation. I can use a fixed orientation constraint, which I think makes perfect sense, at least for cortical sources. But if you think that that's not appropriate, for example, you don't trust your cortical segmentation, so there might be errors and it might not get the orientation right, or you may think that, well, certain sources might not flow perpendicular to the cortex, you can choose something in between. So you have, for example, an option to say, I want it mostly to be perpendicular to the cortical surface, but I will allow some variance. Let's say 20% of the variance can be also tangential to that direction here. Yeah, so this is called loose orientation constraint in MNE-Python, which is usually the standard one. And in the end, when you have a result, I mean, using this loose orientation constraint, you can still plot your result as as arrows. You still get an orientation, but you might still choose to just use the intensity at the end. So you don't necessarily have to use this information for whatever you want to do with your source estimate at the end. And we will talk about some of these things again when we actually talk about source estimation and the different options that you can choose there.